Thanks. And I'll start with some good news and some bad news, right? The good news is my Wi-Fi doesn't work here, right? And even my phone doesn't work. I want to do a demo. So I went to the front desk and said, I live in Sweden, it's a Swedish hotel, give me the password. They gave me the password. So I got the Wi-Fi password. The bad news, I'm going to give it to you at the end, because if you start surfing it, my demo mightn't work. Okay, so I'm worried about that. But anyway, and I'm going to talk, if those of you who were at the last talk, this will be kind of a continuation of what Ritik was talking about. I'm going to talk about a new area called serverless machine learning. And I'll just tell you about that before I get started. So I have a course called serverlessml.org. It's free. It's building serverless machine learning systems for free on technologies like GitHub Actions, GitHub Pages. I showed earlier, I'm going to do a demo with the new technology called Modal for serverless compute. It's like Lambda, but it's nice. It works. No IAM roles, no S3 buckets to configure. You just run it. And then also user interfaces like Hugging Face. And I'm actually going to work on the similar demo. I'm going to work on the Iris data set. For those of you who were at the previous talk, you'll know what that is. And I'll show you how we can do end-to-end machine learning. And I'm going to throw in a bit about data validation. So the talk is primarily about data validation, feature stores, but I'm going to weave in all of that in it. So if you're here and you're interested in data validation, maybe you're a data engineer and you kind of go, it's obvious. My job is to make good data available for data scientists, so I care about data validation. If you're a data scientist, on the other hand, and you're here to learn about data validation, I would say the first thing you should be doing is getting a working system. Data validation comes after, right? Data validation is you get to your work. It's like if you're a proper I didn't mean to offend anyone. If you're a software engineer, the first thing you do is build a working system. So you get a working system, and then you build layers on top of it. We do it all the time. I'm a systems guy. You build the tiniest thing you can, work it, test it, then add layers on. So testing is really about the second part. So this is validate features. So I'm going to talk primarily about how we validate data coming into machine learning platforms with a library called Great Expectations. So this is a hierarchy of needs, right? Yeah, I think the first thing you need to do is get your AI app at the top built. You have some raw data at the bottom. You're going to create features from it. But once your system is running, you need to be able to rely on the features that feed your models, and you need to be able to rely on your models. Now, I'm not going to talk about testing models today. I'm going to be talking about testing the features that feed the models. Okay? Now, those of you who see this diagram will go, this is a complete gross simplification of what testing means in machine learning. I've read the D. Scully paper. I know there's a lot of detail. So I'm going to show you the detail, and you don't need to be too scared. This is a kind of a generic architecture for an operational machine learning platform that you'll see in the enterprise. This is what we call the data for AI flywheel pattern. What it basically means is, if I've got an operational machine learning system that's running 24/7, predictions are being made, I should be logging those predictions, using that to create new data, the new training data, the features. There'll be training models. We'll be deploying them to production, and we'll be generating more predictions, generating more training data, and the thing just gets better. So this pattern of data for a flywheel is what you kind of want to build. But if you want to build this, you need to test at every point here, a lot of testing. So you can see all the tests that I've just added here, and I'm only going to talk about one of them today. So I'm going to talk about runtime data validation. So when you're creating features, how do we validate the data that we're going to feed in for both training and serving? And in enterprise AI today, we use a feature store to manage our data for training and serving. It stores the features. You can see there's an online API directly to serving, and there's an offline API for batch applications or for creating training data. So that's what we're going to do, okay? So I'm going to start at the beginning. Imagine you have a lot of enterprise data, many different data sources, and you're thinking, I'm going to train some models. I'm going to use features also for online models. I'm going to also use features for batch models, for analytical applications. Maybe they run once a day, once an hour, and make predictions. So what you start doing is you start getting data from your back-end systems, engineering some features, and maybe even you validate the data, make sure there's no missing data, the usual kind of 90% of data science work of cleaning up your data. But what you end up with often in this case is, at the very bottom it says one monolithic feature pipeline per model. Okay? If I want to deploy a new model, I write a new pipeline. Now, that seems okay. You're thinking, okay, I'm deploying 10 models, we're fine. But large enterprises that we work with, they deploy thousands of models, not just one or two. And thousands of pipelines pretty quickly becomes unmaintainable. So the pipeline, this feature pipeline, which creates the features both for training and serving, it's basically a program. And typically it's Python or PyCon. So it's going to be a Python program. And it's going to execute a number of steps. It's going to read the data. I have this pattern I call VASE. It's going to validate the data. And then the type of feature engineering steps I can do, I can compute aggregations. If, for example, I have hotel room bookings as my raw data, and I want to look at maybe the amount of money I'm going to make on this hotel room in the hotel chain, I'm going to compute the vacancy rate. So it's going to be an aggregation over hotel rooms. You know, what's the vacancy rate per week? And maybe I'll consider seasonality and many other factors. Other things you might do is dimensionality reduction. You know, you might be using embeddings. You might be doing feature extraction with binning, crossing, and so on. All the things you would typically do in feature engineering. And the output will be typically a data frame of features, whether it's Python data frame, a Pandas data frame, or a Spark data frame. And you'll make that available for training and serving in a feature store. So the other part I'm going to talk about is Great Expectations. Now, there are many libraries for validating data. You can, you know, look for missing data in Pandas. That's great. But Great Expectations has a very rich set of functions, or what we call expectations, that you can apply to your data. And I've just given an example of a few of them here. So if you have some data coming in, if you're writing it in Python, it's a dynamically typed programming language. We don't have static typing, so you still might need to check that, you know, it's passing a string of 1 instead of the integer 1 is not good, right? For example, you might have a range of values that are valid. I'm going to give an example later in the iris flower data set. It uses 4 features: the length of a petal, the width of the petal, and the length of a sepal and the width of the petal. And you can say, well, the range of these petals and sepals falls within, you know, 0.3 to 10 centimeters. And if any value comes in outside that range, I probably have an error. If I have some missing data, I might have an error. I might have a new category appears for a categorical feature or a categorical variable, and that's probably not good if it appears in runtime. Maybe I could map it to another category, but if it's completely new, that's not great. And maybe I have an expectation over all of the data frame I'm going to write. Maybe I want to say, you know, if this feature should be here, this name. Maybe the average value of a given feature should fall within this range or something like that. So there's many different expectations you can define. And if we look earlier, I said this is applied not in training, this is applied in production. So in a production system, that means, and if you're building a machine learning system, right, production means basically new data is coming in, right? The whole point of training a model is that there will be some new data arrives, you're going to make predictions with it. Otherwise, there's no point in having a model, you know. And much of the courses we do give you static data sets and say, off you go. Static data set, train your model, evaluate it on the test set, you're done, right? But in the real world, you need to have new data coming in all the time. So, for example, in the service machine learning course, we generate synthetic data to make it easy for you for the iris data set. So it's going to generate synthetic flowers the whole time. But it simulates new data coming in. And then with new data, you can apply things like these tests. You can say, okay, new iris flower came in. Are the range of petal lengths and sepal lengths valid or not? And if they're not, you can basically say, well, I'm not going to ingest this data because I don't want to have garbage in my feature store, because garbage in, garbage out. Okay, let's look at the code for Great Expectations. And many of you who work in data science and Python will be working in Pandas. So what you can typically do is you can have your data in a Pandas data frame and define what we call expectations, either on the table or on individual columns. So in this example here, we can see we have a column called age at transaction. So we maybe have a financial transaction, maybe it's a credit card transaction, and the expectation type, and there's as I said, there's a number of expectation types supported in Great Expectations. It's saying the column value, the minimum column value to be between, and it's going to supply 2 values, a min and a max. So the minimum value for this age at transaction should be between 18 and 130. So it's probably a human age. And then when you apply that to all of the rows in your Pandas data frame for that column, the column called age at transaction, you'll get a result. And this result here is your validation result. It's basically saying, hey, the observed value was 17. It was at this particular point in the data set, and the success was false. So we had a value that we ingested that was outside that range, and we get an error. So that's the basic idea behind Great Expectations. You can define expectations, write some data, and then you can basically say, well, what are you going to do about it? You can ingest the data and give a warning, or you're going to say, I'm not going to ingest the data, I'm going to fix it before I ingest it.
This is like an assertion on data.
It's an assertion on data, yes. And it's run at runtime, as I said before. So the point of the feature store in this architecture is, as I mentioned before, you don't have one pipeline per model. Sorry, this is really sensitive here. We're back. Okay, so we're going to have, every time we have features defined that are going to be reused across models, we just write them to the feature store. And we're going to use great expectation to validate the data as it comes in. And then downstream, you can have data scientists who are training models. You can have batch applications getting batches of features to score. And then you can have online applications as well, returning rows of features that they're going to put together in feature vectors to make predictions with. So we decouple models from feature pipelines. So now the feature engineering code runs on the left, the training code runs on the right, and the inference code runs on the right. So we no longer have a single monolithic end-to-end machine learning pipeline. I normally say there are no machine learning pipelines or end-to-end machine learning pipelines. There's a feature pipeline, there's a training pipeline, and an inference pipeline. And they all should run at their own cadence. Okay, so then if you have this architecture, maybe you have another feature store, and there's a talk later today about a feature store in the afternoon. And in the case of that feature store, you say, well, maybe I want to add expectation support. So there's no expectation support, or there may be actually right now, but what you would need to do is if you're running great expectations and you're going to run it by yourself, and maybe you're not using a feature store, maybe you're using just some data platform, well, you run your great expectation code. It will give us our output, this JSON file, the validation report. We'll have to define our expectation suite. And then you have the challenge of, well, how do I make these results available to developers and also people operating the system? Because if you have a feature pipeline, it'll run as often as new data is being created. So maybe new data is arriving every day or every hour. The feature results or validation reports should be available every hour and every day, and you need to be able to access them. So what we did for this is we moved it into Hopsworks. And there's a second challenge apart from accessing just the validation history, which is the code on the left. If I'm embedding all of this expectation code and logic in my feature engineering pipeline, it can make the code verbose and more difficult to read. So we're going to look at how we address that. And then finally, great expectations doesn't give you alerting. So if there is a problem, you still need to somehow tell people there's a problem. So I mentioned there's other feature stores, and there is one other feature store, and they do validation after the feature store, which we think is insane, right? You should validate data before it goes into the feature store. So what we've done is we've integrated great expectations with the Hopsworks feature store. It's open source. It's available as a serverless platform for free right now, and you can deploy it in your own cloud, your own private cloud. And it also gives you the ability to do alerts as well. So what I'm going to show you briefly is that firstly we can make the feature pipeline simpler by having declarative expectations. So instead of having the expectation attached to the feature engineering logic, I can say, well, I have a table here called the feature group. I'm going to attach that feature engineering logic to the table, and then when I write, it'll just apply those expectations. And then if I want to do alerting, the alerting will be done by the platform for me. And then the platform will also store the validation history, so I can just look it up. So I don't need to run and install any new platforms. Okay, let's have a look at the API for great expectations and feature groups. So Hopsworks is it's a feature store. Now I've mentioned already that a feature store, one of the goals of a feature store is to be a data warehouse for features. You kind of have this centralized platform where you can go and look for features, reuse them across different models. There's also some other low-level technical problems it solves related to. You can see we have an online API to get an individual feature vector. So maybe, for example, I'm doing credit card fraud, right? And if I'm doing credit card fraud, I might start out and say, well, I'm going to take all of yesterday's credit card fraud or credit card transactions, and I'm going to score them for, whether I suspect individual transactions are fraudulent or not. So maybe I do that on a batch. Maybe I have 10 million transactions to score. So I use the offline API, get 10 million rows, score them with my model, and then I'm done. But if I want to say, okay, that's working really well, we're happy with the model, now I want to do it live, real time. When a transaction comes in, I want to score it, and I've got 20 millisecond budget to do that. So then what the feature store gives you is a low latency API to retrieve individual feature vectors. So if a credit card transaction arrives, I take the credit card number, and that's going to be a primary key to this view on my tables, this feature view. And I'll say, give me back all the features related to this credit card. So for example, how often was the credit card used in the last hour, the last day, the last week? Where was it used? The feature store will store that historical features that your stateless application over here won't know about. So it won't know the history of the credit card. It won't know if there's a lot of fraud going on in a specific area, so the contextual features. So the feature store stores those historical features, contextual features, and they're filled by these pipelines that can run in the background. So every time you use your credit card, there's writes coming into the feature store, and those features become available for making predictions with, but also for creating training data with. So in our particular feature store, Hopsworks, we write to things called tables or feature groups, and then you have many different tables containing features. But when you want to train a model, you may have features from this table, this table, this table. So we have a logical view that says, these are the features I'm going to use in my model. So you create a view which represents the features used in a model. And these are stateless, but they're just a representation of features from many different tables. Okay, so this is how we're going to look primarily at how we write data, because that's data validation. I'm not going to talk too much about reading data. So let's have a quick look at some code. Now, what we can do here in Hopsworks is, I said already, that we can declaratively attach expectations to these tables or feature groups. So what I do at the top here, in Great Expectations, you have an expectation suite. That is basically, think of it as being a number of expectation rules. So you create your expectation suite first, and then you add individual expectations to them. So in this case, I have an expectation called expect column value to be between, and then the kwargs are the name of the column and then the minimum value. So obviously I should add a maximum value there because I just hacked this out. And then I attach this to a feature group. So when I get or create a feature group, when I create it for the first time, I can say this is the expectation suite that's associated with it. And every time I insert my data frame, it's going to run those data validation checks, and it'll register the data validation results with Hopsworks. So I get them from there. Okay, so what we see then in the platform is the data validation results. So I've got I'll do a demo. I think I have time for it so we can see what it looks like. But you can see here, you can see the historical set of results of the feature pipelines. So the feature pipelines ran here, and they were successful, but we had some errors as well. And then you can obviously drill down into individual results and say, okay, what happened in this particular case when this feature pipeline run failed? Well, you can see, well, this particular check failed, and this is why it failed. And then if you need to alert, you can define alerts on your data ingestions and say, okay, send an email to this address or send a message to a Slack channel. So if you want to, you say, okay, this sounds good. I'm kind of happy with this. I'm going to, I've built some machine learning models and run them in production, but we need to, do more testing. You'll probably think about doing some ML ops, some machine learning operations, some automated testing of your features and models. Now, if we look at testing of features or feature pipelines, not models, the kind of things that you would do is you would say, okay, I'm going to test the individual features. I'm going to define unit tests with PyTest to make sure that the logic of a feature is stable. I'll do integration tests of pipelines to make sure I can write the whole pipeline and it works to the feature store. And then I'll add great expectations to that to make sure that the data being written is correct. Now, I said to you already that the great expectations of data validation is a runtime test, and this is not runtime, right? This is run when I'm developing my code. I run the test. So one thing you can do, and this is what we encourage people to do, is that you want to also test your expectations. You don't just want to say, okay, here's my expectation, deploy it to prod, we're done, and then if there's an error in your expectation, well, you have an error in prod. So what you can do is you can take the data that your feature pipeline works with, take a subsample of it, check it into Git even, and then run the great expectations against that subsample data. So what it'll basically be doing is testing to make sure that these validation rules work against this subsample data that you have. And in that way, you can also validate that the expectations work on your data as you expect. And then this can be put into a kind of Jenkins CI/CD pipeline where you can then move from dev to staging to prod. Okay, I'm going to do a demo. I think I've got a few minutes. And we'll have a look at the following type of demo, right? So if any of you were at Ritik's talk, the last talk where he talked about fast API, it was very interesting. You have to define that's how to make a model available for serving. In the course, in the first lecture, we do that, right? But what we also do is we do batch serving models as well, and we do monitoring. So I'm going to show some new technologies today that in the course we use GitHub Actions and GitHub Pages. So GitHub Actions to compute the feature pipelines, because everyone's got a free GitHub account. And if you don't know GitHub Actions, you can run Python programs, I think 3,000 hours per month. It's very generous. But there's another cool platform called Modal. It's a Swedish guy out of New York. And he's giving a talk at my course next week, actually, Eric Bernhardsson. And he did machine learning at Spotify, the recommender system. He also did Luigi workflow pipeline. What his company are doing is a platform called Modal, which gives you serverless compute. And you can use GPUs. You can do it for feature engineering. You can do it for model training. And you can also do it for batch inference. What also is really cool, if you're not aware of it, is Hugging Face give you free user interfaces. They give you 2 CPUs and 16 gigabytes of memory to build a user interface, and currently it's free. And then we have this Hopsworks platform that we build, which is a stateful layer for all of this, because if you're computing features in your feature pipelines and you're writing them to, you need to store them somewhere, because we've now separated out the feature pipeline from the training pipeline and the inference pipeline. Feature pipeline is an operational system. It's going to have to run at a cadence. So if I have a system that new data is coming in every hour, I need to schedule the feature pipeline to run every hour. Training doesn't need to run operationally. It can run whenever it needs to. When the models become stale, we'll run the training pipeline. And then if I'm doing batch inference, I can schedule the batch inference pipeline to run when it needs to run. And maybe it doesn't need to run every hour. Maybe it's once per night. If I'm doing an online model, well, then I'll have an online model that will retrieve features in the feature store to build up feature vectors to make predictions from a UI. So I'm going to show a quick example of this pipeline, and then we'll kind of we'll finish up. And so that's the course. And let's look at that. Let's go down here. OK. So there's actually 2 user interfaces for this pipeline. One is it's predictive analytics, where we can basically put in values for this petal length and the sepal length and the petal width and sepal width, and then it'll predict what type of flower we have. Now, I don't have my glasses on here, so I'm kind of going in the dark, but let's just see what happens if I change some numbers here. That's saying it's a Virginica. Now I get versicolor, and if I change them around, I get probably a Setosa. So what training a model does like this, when you have an interactive UI to it, is that you're able to ask questions to the model. You say, well, what would happen? What type of flower would I get if I put in these feature values? So you can think of any kind of, in the course I'm teaching KTH, the lab they have now is use the Titanic data set. And then you have to enter like the details of the passenger. Is it a man who's like this age and was traveling 3rd class? Did that person survive, yes or no? So, but you can think of any kind of predictive analytics problem and do it that way. You can also think of this as a serverless machine learning platform that once per day generates a random flower. This is a different Hugging Face space. So today it generated a flower, and the model predicted it was Iris setosa, and I have the label because I generated it with synthetic data. That's the one it predicted. And then I can see the history of the prediction. So the history I wrote as a data frame back to the feature store. When I make predictions and I have the label, I write them in there. And then I also store the confusion matrix, which tells us the performance of the model over time. And historical performance over all the predictions. So I can see where the model predicted incorrectly. So here it predicted versicolor, but the true was Virginica. And here it predicted Setosa 3 times, but it was actually versicolor. So my model's not very good, but that's OK. Right, so let's have a look at this code, and we'll look at the Great Expectations code behind it. OK, I have this one open here. Right, so the first thing I need is a feature pipeline. So this is my, hopefully you can see this code. This is the entire feature pipeline. So what I do is I'm downloading the iris flower as a data frame, that data set. I create the feature group for it, and I'm just putting that data into the feature store. And then I could have defined this expectation suite after or before, but I just decided to define it afterwards, and then I attach it to the feature group. So I'm saving that expectation to the feature group. And all this expectation suite says is the sepal length and sepal width and petal length and petal width should fall within these ranges. Okay, so so that's basically it, right? So I ran that already, and where are we going? So then I have a different pipeline which is going to generate a random flower every day, right? And this is going to run on Modal, and I'll actually run it in the background so we can see it. And what this does is it generates a random iris flower, and then it writes it. It gets a reference to our feature group, and then it writes it to the feature store. So you can see there's no Great Expectation code defined here because we've attached it declaratively to the feature group. It gets applied in the background. So let's have a look here. So what this is doing now is it's looking at the bottom there. It's actually launching a container in the cloud. And I launched this earlier, so it was cached, and now it's completed, right? And in Modal, I could have run 10 containers in parallel, and it would run that fast. And the code, if we look at the code in detail again, I'll just explain the code. This is the code that got run. When I'm testing, what I typically do is I set this environment, or set local, this variable to be true, means just run this function. So it's going to run on my laptop. If I run it in the cloud and I set local to false, it calls this f function with the stub run. And the f function up here, it's just an annotated function. So you can see what it's doing is it's saying I want an image, and on the previous line we had saying the image is going to be a Debian image, and I'm going to install Hopsworks 304. And I'm going to schedule it to run. I want to schedule this to run every day, so I specify a period. And I need an API key to write to Hopsworks, so I get that API key in Modal. Okay? I pasted that into Modal and I get it from there. So now this thing can run. It'll run once a day, right? You don't have to pay. It's actually free right now, but it's very cheap. I think the plan is for it to be quite inexpensive. So that's going to write the data to our platform. And if I want to generate this particular output, which is the predictions, the flower that's generated today, the prediction for it, and then the historical predictions, I have a different pipeline called the batch inference pipeline. Well, the batch inference pipeline is a little bit more complex, but it's doing the same thing. I have this function g, which I can run locally, or I can run it in Modal. I need a few more libraries in here because I'm doing a few more things. I'm generating some PNG files I'm going to upload to Hopsworks, both for the data frame and for my confusion matrix. And what it does is it gets a batch of data from the feature view in Hopsworks. This is the data I want to score. I predict a flower. I have a URL where those flowers are shown. And then I download the flower, I upload the flower to Hopsworks, I write my predictions to a feature group, and then I keep going, and then I'm kind of done, right? So what this batch inference pipeline has done is just written the state to Hopsworks. And let's have a look at what that looks like, because I think I have it open here, somewhere here. Here's Hopsworks. So this is Hopsworks here. And like I said, it's a serverless platform. You can deploy it in your own account, but I have all these feature groups here. So I have this one called Iris, but the Modal one is called Iris Modal, actually, I think. So that looks down here. So every time I write to this platform here, I can see the features that are in there. I can see the activity in here over time. You can see I'm doing a lot of writes. We can go back and we can get a preview of the data that's in there when you write it. So you want to maybe see what it looks like. There's some of the data in there. We can get statistics over the data. So every time we write data, we compute descriptive statistics, so we can see easily the min, max values of the different features here and the mean and so on. And if we go back to, this one here, Iris Modal, we also have the expectations here, right? So if I look at the expectations, when I write the data, you can see that it's maybe hard to read there. You see there were 4 successful. So it validated the 4 feature values as it ingested the data. And you can have a look at the report, and it was success, and everything looks to be good. OK, and then the model is stored in here as well. We've got a model registry here, so I have 4 versions of that. And you can deploy models for serving here as well. And then the last thing I'm going to show is the app here on Hugging Face. So this is the program that actually renders that particular web page. It just goes to Hopsworks connects. So I have to put an API key in Hugging Face. It downloads those images that I generated, and then shows them on the page. And that's pretty it. So it's all done in Python and all on free serverless services. So that's it. That's I think I don't know how I'm doing for time, but I'm around okay. If you want to learn more about this, there's a course called Serverless ML. I'm going to talk about expectations. The video will be out on Tuesday or Wednesday this week, but there's 4 episodes already on how to do this end-to-end in the first one, and then feature engineering, and then training, and then user interfaces. And then we're going to go into MLOps, and then into real-time machine learning.
Thanks so much. I have a question regarding like the Hopsworks actually back end.
Yeah.
It's not clear for me. Is there any actual data that you guys host?
Yes.
Or I mean.
So I can explain it briefly. So the way the platform works is that you have these things called projects, and they're private. So when I create an account here, I get a project on the platform. It's private for you. No one else can access it. You can share data from it, features with other people if you want. but it's stored in our backend. It's in a bucket in S3. So if I get into the details, so if we actually want to get into the details of, well, if I'm writing data to a feature group, so if we go back to our iris one there, the iris modal one there, we can see here that we have a bit more in here. We have all of these updates that we make. So you can see I've made a row and a row, and you can see there's a commit ID for it as well. So actually storing it as hoodie tables on a bucket in S3. So that means you can do things like time travel. Give me the state of this feature group at that commit, and you can read that up. And you can say, give me the changes in this range of data. So it's doing all that stuff at the back end. And then if the data is also available by the online API, we have our own database called RonDB that we develop, which is a fork of, we develop it. So the main guy from MySQL works with us, Mika Ronström. And that's an in-memory, low-latency, highly available database. I worked on that team as well. So we're a bunch of ex-MySQL people as well.
Thank you so much.
Thanks, very interesting. I'm just wondering about like computer vision and NLP, ML projects. Do you have any thoughts on how, is there kind of the same kind of workflow for those kind of domains? Do you have any plans to get into that, or what's around at the moment?
Yeah, there's two workloads there, NLP and vision. Because maybe use transformers, but both are a little bit different, you know. So feature stores are primarily used for tabular data. I should mention that. So at the back end, we're storing the data in Parquet tables and Parquet data in hoodie tables. You can store images in there, but it's not maybe the most efficient way, because images have specialized file formats and different ways of processing them. So I wouldn't say people are using image data particularly much in feature stores. You can do it, of course, right, but it's not the most efficient way to manage that data. So what we've seen a kind of bifurcation in the machine learning space where there's platforms that handle image data and vision data, and they're really specialized for that. And this is more enterprise tabular data. NLP is somewhere in the middle because you've got a bunch of text. So we have a lot of NLP use cases. We have customers doing a lot of NLP. So in Sweden, there's a national employment agency. You upload your CV there. It's extracting all the data, writing it to our platform, doing predictions with transformers as to, matching up employers to employees. That's pretty common use case, because often when you're doing NLP on a document, you'll have additional features that will help you. So you'll know about the person who's uploading the documents, who's looking for a job, maybe their background, their age, their skills, and so on, where they're located, and those features will help, as well as the features you extract from the text. So for NLP, it's quite widely used, because the data is all stored in S3, it's cheap, so that's okay. And other one is like, call center data. So transcribed call center data is like huge amounts of it that's also used in feature stores.
Thanks for the talk. I was wondering about expectations.
Yeah.
You invest so much energy into repeatedly asserting that the customer isn't trying to inference and junk. Like another way to do it, you could train the model explicitly. You can augment the training data and just say, deliberately predict an invalidated class or a junk class, whatever, Sentinel -1 or 999.
Yeah.
The flower is something we've never seen. For the credit card, it would be invalid or weird features. Why is it so important to sort of repeatedly trigger if the customer is submitting junk data?
So you touch on a very important point. I haven't said that you can train a model so that it's robust against bad data, right? But not all types of bad data. So there's certain types of bad data you can make it robust against, and certain types you can't, and it depends on the model you use. So often what you'll need is very sophisticated data scientists who have an insight about the data. They know there's data missing here, they know that, and they have to take that into account when they train the model. Yes? So that means you have, it's a more complex model training process. And in large organizations, they'll kind of say, okay, well, it's easier just to make sure the data is correct before it gets in. Then there's the other issue is runtime data. So if I have data coming in, it's an online request, and the users maybe enter in the web page, where am I going to validate that data? I can validate it in the web page. I can validate it in the inference pipeline. It's up to you. So you can do this also in inference. I didn't talk about it for kind of the inference case, but it's not the common case. The common case is for feature pipelines.
Sure, but...
And the other one I didn't talk about, sorry, is asynchronous. So you can actually profile your data. So if you write a bunch of data to a feature group, you can say with great expectations, please profile it, generate some rules for me, and then those rules can get applied on new data. So it's quite flexible that way.
Sure, but it seems to me you're conflating different cases. Like a customer with an age of -20 is always wrong. A customer with a credit card with an age of 3 is probably wrong, or an age of 200. But in the flowers, they could well be like features for Venus flytrap, like something you haven't seen yet. So you're kind of conflating the generalization case against the
I agree. I chose this particular use case because people are familiar with it. I didn't want to produce two abstractions at once. But sure, if I have credit card data and I have a credit card payment and it's negative, what do you want to do? Do you want to make your model robust to it, or you just want to say, I'm not going to predict with it or train with it?
You could predict the confidence number. You can say, we predict this, but our confidence is only 23%.
I think most teams, if you have data coming in and there's something wrong with the data source, for example, if I have credit card payments coming in, transactions, and let's just take the example that the amount of money being paid in is negative, but it's coming from a credit card machine, so that shouldn't happen ever. So it would make sense to flag that before it ends up in your feature store rather than train models to be robust against it. That's my opinion on that particular matter.
Okay, so it's all predicated on the attitude, like we're not just inferencing, we're extracting features for the feature store.
Because we're would you train your model on bad data, effectively? And you might have to, and there's whole companies who do take poor quality data, that help make it better. It's a big space by itself.
Well, it's broken by construction. I mean, if the customer's
But I think in tabular data, in particular where you're in high-value use cases, like we work with insurance companies who do risk prediction and so on, they're very conservative now when it comes to the data coming in. So they don't want, anything strange there.
Mm-hmm. Okay, thanks.
Any further questions?
Separate question for you. How would you compare modal? So you were saying modal is free serverless compute. How would you compare it to AWS Lambda or other?
My thing is, modal is what Lambda should have been, right? So now if I want to use Lambda to do anything, it's very complex, right, to set up, particularly for Python. So they've added something called AWS Chalice. I don't know if you've seen it. It's kind of a layer on top of modal. In AWS Chalice, you just put into your GitHub repo a requirements.txt file, the libraries I want, and then you write your code. But Modal does a lot more, right? So it gives you, GPUs. It allows you to run things in parallel. It allows you to do scheduling that I talked about, so workflow scheduling, at a very high level, and it's super fast, right? It's like blindingly fast. It's what it does there. It caches my container, and if you've seen the container before, it just loads it from a very fast, low latency file system they have. So I've done a lot of low level engineering to make the thing very responsive. And the last thing that's cool in it is to get your proper Python stack trace. So if I have a mistake, it'll give me a proper Python stack trace so I can debug what happened. And in Lambda, good luck with that, And what I like about it, at least with our platform, is I can run the code on my laptop. And I'm doing this with students, run it on your laptop, and then when you're happy, just run it in Modal. So it's very easy. And I don't know how easy it is to do that in Chalice, for example. Thank you.